Now we'll look at naming compounds and nanotechnology. When chemists from different areas of the world were studying chemistry, they would often repeat the chemistry somebody else had done and think they were the first to get to it. And the reason this was happening is because they had different ways of naming chemical compounds. So when they'd go to look in the literature to see if something had been done before, they would use their own language, and they would not find that somebody else had already done what they were trying to do, and then there would be arguments over it. So they got together and decided they needed to come up with a systematic way of naming compounds, so that if you were in China, or you were in Russia, or you were in Germany, or you were in the US, you could search the materials and see if it had already been done. And they did that. It was called the IUPAC naming system. IUPAC stands for International Union for Pure and Applied Chemistry. And there are two basic ways that they name compounds that we'll be working with in this class. There are two kinds of compounds. One is called ionic, and the other one is called covalent. The ionic compounds are made of a metal and nonmetal in some proportions. So if you remember on your periodic table, they're labeled. The metals were your lower left-hand side, and your nonmetals were the upper right-hand side. When you have one from each section, you get an ionic compound. And to name those, you write the name of the metal, just as it is on the periodic table, and then you leave a space. And then you write the name of the nonmetal, regardless of how many they have of each type, and you change the ending on the nonmetal to IDE. So if I were to take one atom of sodium, one atom of chlorine, combine them together, I would call that sodium chloride. So notice the chlorine changed to chloride. If I take lithium and oxygen, they happen to combine in a 2-to-1 ratio, but we would still call that lithium oxide. And the reason we don't put prefixes there is the ratios they combine in are always the same. You can look at the math of the charges they have and determine how they'll combine. And so we don't have to say how many are there. Once we learn those charges, we can predict how they'll combine. But for the sake of what we're learning here, just know that when you got a metal and a nonmetal, you don't have to indicate how many you have of each. You just write the name of the metal, nonmetal, with an IDE ending. So if we combine aluminum and oxygen, they happen to combine in a 2-to-3 ratio, but you would still just call it aluminum oxide. When you have a covalent compound, you'll have two of the nonmetal elements that have combined together. Now, when nonmetals combine with other nonmetals, their charges are not as predictable. So they can combine in a variety of ways. And because of that, we now have to indicate how many we have of each. So they do that with prefixes. Mono would be 1, di would be 2, tri is 3, tetra is 4. And you say specifically how many of each type of element you have going on. So mono isn't used if the first element there's only one. That's because often in chemicals you'll have an element in the center of your compound, and so there will just be one. Because that's so common, we don't put a mono there, but if it's the second element that we just have one of, then we do put mono there. If there's no prefix, it's assumed to be one for the first compound or the first element. So for example, if I have one nitrogen and one oxygen, well, it's pretty normal to just have one of the first element, so I don't put mono, I just write nitrogen. But it's not as common to have just one of the second element, so we'll say monoxide. Monoxide. And you'll notice, although mono has an O and oxygen has an O, they just reduce it to one O. Oxygens are a tricky one there. It's because monoxide would just be a mouthful, so they just say monoxide. If you have an oxygen and it's got a prefix, you can remove an O or an A from that prefix, but you leave the I's in. So it would be tetroxide, monoxide, but not doxide. You keep the I in there, so it'd be dioxide. So here we have nitrogen monoxide. If you have 2 nitrogens and 4 oxygens combined together, that would be dinitrogen tetroxide. If I have 1 nitrogen and 2 oxygens, that becomes nitrogen dioxide. If I have 1 phosphorus, 3 chlorines, I don't need the mono on the first one because that's pretty common. I say phosphorus, and then I say trichloride. Nanotechnology is an area of chemistry that is up and blooming at the moment. It was proposed in about 1959 by someone, but we only really started doing intense research on this in the late 1980s, early 1990s. And there are the gist of what it is as we shrink technology down, we can get smaller cell phones, smaller computers, more memory, all that kind of thing. But we get to a limit in what we can do in the standard ways we've been doing, because we've been doing it in the area of your microtechnology, of a micron. And that's because that's where your light can look at things, that's where your electrons can look for defects, all that kind of thing. And so the proposal is, if we could get down to the size of molecules and build our machines with molecules instead of with groups of molecules, then we can make things really tiny and maybe even hook them up to living molecules, animals, human bodies, the brain, all that kind of thing. So they approach this 2 different ways. One is they do top-down research. The people who are working with the microtechnology, let's see how we can slowly make that smaller and smaller and smaller and smaller till we get down to nano. And then there's also bottom-up research where they're trying to make various components of switches and machines and things like that out of molecules. So they'll invent something that turns a rotation, so it's kind of like a cog, or something that rolls along, so it's kind of like a wheel. And they'll do it on a molecular level, and then they'll say, okay, here's one more piece that we can add to our collection of our nanotechnology. The end goal is to make things that are very tiny or that can do massive projects without taking up a lot of space, and perhaps to integrate them with human biology or some sort of animal biology. So those are the 2 end goals that they have with the nanotechnology.